everyone, welcome back. Mrs. Henderson here again to show you a little bit more about the miraculous world of water. So I wanted to talk a little bit about heat and kinetic energy and movement, and a little bit about kind of what water behaves like when it's a liquid versus when it's a solid versus when it's a gas. And it is a kind of this really strange molecule that when it is really, really cold, when it doesn't have much energy, it's going to behave in a way that is kind of different. What happens is the hydrogen bonds become really stable and it forms this really kind of spacious, you can see all the holes in there, crystalline structure. And this is what ice is. Ice is actually less dense than water. It's one of the only things that spreads out when it freezes in all of the molecules that we know. And when it does that, it actually allows ice to float on top of water, which is super important for a lot of living organisms that have to overwinter in like frozen ponds and lakes. They wouldn't survive if they froze, but because water insulates the surface, they can survive in that slightly warmer water underneath. I still wouldn't want to be one of those creatures, but they don't die in the winter. When it heats up, it starts to move. So heat and movement are very closely related. And you might remember that heat is a type of kinetic energy. Kinetic energy, movement energy. So at absolute zero, that water is frozen into this crystalline structure. But as it starts to get more energy, it starts to move. And as it starts to move, you'll notice it's kind of more compact than it was before because it's making those bonds and breaking those bonds as those molecules are moving around each other. The hotter it gets, the faster the molecules move, and pretty soon they're moving so fast that we start having molecules escape. And when those molecules escape, that's when they're becoming gas, when they're turning from liquid water into water vapor, when they get enough energy to break those hydrogen bonds and to fly out into the atmosphere. So that's kind of how kinetic energy, how movement of molecules as they heat up creates kind of what we see in terms of the solid ice that floats on the water, and then the liquid water that starts, you can imagine it boiling at the surface, and then eventually starts to escape as those molecules of steam. What's cool about this is that water has a very, very high, two things actually, heat capacity and then heat of vaporization. Because the bonds have to break in order for it to move, it's hard to get it moving. And so you have to put a lot of heat into water in order to be able to make it heat up. It has a very high heat capacity, meaning it can absorb large amounts of water before it moves into that next state. It takes a lot of energy to heat up a gram of water. It actually has the highest heat capacity of all of the elements that we know. And it also has a high heat of vaporization, meaning it takes also a lot of energy to move it from the the liquid, where it's moving like crazy, to where it actually breaks the bonds and escapes out into the atmosphere. So it takes a lot of energy to evaporate water to be able to do that. And that helps animals all the time with like cooling down. So your sweat actually cools you down through this evaporative cooling, that the water molecule takes the heat with it when it leaves your body, which is why on a hot day, if you get wet, you tend to get yourself cool very, very quickly. Okay, so I'm going to show you this in action because it's kind of cool, and I'm going to make a big mess, so I'm going to apologize for that in advance. I've got balloons. This one has air in it, and I've got flame. So what do you think is going to happen when I put flame next to this balloon? So make a quick prediction. What do you think is going to happen when I do that in a second? Okay, I'm guessing it didn't take you very long to figure that out, so I'm going to go ahead and do it. So as I put it next to the flame, just as probably you expected, it's going to pop, right? The plastic is just really susceptible. It melts. It's going to make it so that that balloon is going to pop very quickly. And I've got now the remnants of my poor little pop balloon. This is a water balloon. So, and remember, water has this ability to absorb heat. So make a prediction. What do you think is going to happen when I do the exact same thing, but this time with a balloon filled with water? So make your prediction, see what you think might happen because of the specific heat capacity, the ability of water to absorb a lot of heat energy before it gets hot itself. Okay, should we try it? All right, here we go. So same flame, and here's my balloon filled with water. And you can see my balloon filled with water, even though it has that flame on it, doesn't. Look, you can even see the carbon that's released from the hydrocarbons that just is collecting on the surface of the balloon. Because of the water, it didn't heat up enough. It didn't make the latex hot enough for it to actually melt and burst. And so that's specific heat capacity. That's the amazing ability of water to absorb large quantities of heat and really, really important for like coastal climates and organisms who live in the water, who then have a relatively stable temperature throughout day and night, throughout seasons. Water moderates temperature because it absorbs large quantities of heat and then releases it back during those colder times. All right, thank you. I'll see you next. I think next time we're going to talk about solvents. Okay, bye.